Hello, guys. Good morning. How are you all? Okay, now today the video is all right, as well as the audio. Start. Focus, guys. When is your GATE exam? Your NET exam date is announced second March. No, 2nd March is 1st February. In a month. When is your GATE exam? GATE exam, I think 10th or something. Is the audio clear, guys? Everything is all clear? Can you start? Today we'll be completing superconductor. This is yet another very important topic. So look at this superconductivity phenomena. Mostly everything all right? Are we good to go? From your side, tell me. Okay, so let us talk about superconductivity in the year 1911. 1911, Camerling once discovered that the electrical resistivity of mercury at low temperature, 4.18 Kelvin. So this is the plot of resistivity versus temperature. So if this is the 0 Kelvin temperature, okay. Now when you are coming from this to this, so you are slowly decreasing the temperature. So you see at higher temperature the resistivity is like this, and if you keep on decreasing the temperature at a point of 4.18 Kelvin, you see the resistivity suddenly drops. So at low temperature around 4.18 Kelvin, the resistivity vanishes suddenly. This phenomenon was given the name of, and the temperature that at which this resistivity disappear in zero magnetic field, obviously, is called transition temperature or critical temperature. The transition temperature of mercury is 4.18 material which this phenomenon called superconductor. Now there is a very important property of superconductor which we'll discuss later, that it does not allow the magnetic field lines to pass through it. Okay, like if you consider a normal conductor, okay, magnetic field lines can easily penetrate through it. But if it is a superconductor, magnetic field lines cannot go through this, and that is why you can see it levitates, because the magnetic field lines are repelled. As a result of that, it levitates, and it has a good application. Many places, see, the high-speed train can be built by using this phenomenon. Okay? This kind of phenomenon. You must have seen a video like this will levitate, this will rotate without any physical connection. Now the property which I just talked about, that it expels the magnetic field lines, this property, this effect is known as Meissner effect. As you can see, this is for the normal conductor. Okay? Now you can imagine it, this is for the normal conductor. A conductor can behave like a superconductor under appropriate condition. You see the same material, T greater than Tc, this is beyond critical temperature. Beyond critical temperature, it is behaving like a normal conductor. And as a result of that, you can see the magnetic field lines can penetrate. But as you go below the critical temperature, T less than Tc, as you go below the critical temperature, you can see the magnetic field lines are not able to go through it. So for this case, your magnetic field is not equals to 0. Okay, but here in case of this superconductor, becomes now a superconductor. For this case, the magnetic field will be 0 inside the metal. Okay, this effect is useful to make difference between superconductor and a perfect or normal conductor. So when a superconductor and a perfect conductor are placed in an external magnetic field, the magnetic line of forces do not pass through the superconductor. As you can see in this figure, they are swept away, they are repelled away, thus making the magnetic field B inside the superconductor equal to 0. I have just, while line of magnetic force passes through the perfect conductor and therefore B is not 0 inside the perfect conductor or normal conductor. Okay. Now, if I take, let's say, in CGS unit, if you, what will be the value of B? B, you know, is equals to H plus 4 pi m. This is in CGS unit. So what is the ratio of m upon h for a superconductor? Look, you can say the magnetic field is 0 inside. So 0 is equals to h plus 4 pi m. Okay. From here, m by h is equals to minus 1 by 4 pi. And this ratio of m by h is known as the magnetic susceptibility. So magnetic susceptibility, you can see it is negative. Now, if we do the same thing in SI, unit or MKS unit, the same relationship B is equals to becomes mu naught times H plus M. Okay, this is equals to 0, or H plus M equals to 0, or M by H equals to minus. So in SI unit, the magnetic susceptibility value is minus. So to find the ratio, you can consider the magnitude also. Let's not make it complicated by vectors. Okay. You can just write without vector. If you have given vector sign, then that is also okay. No issue. Chi is known as the magnetic susceptibility. Now, what is the significance of this value of minus 1? H, what is it? Magnetic field in magnetic intensity. And what about M? M is the magnetization. Okay. So this negative value of susceptibility, the negative value of susceptibility, chi is equals to minus 1, shows that the superconductor, this in a CGS unit, in a SI unit, this all we have done for superconductor, where superconductor is not for normal conductor. Negative value of susceptibility shows that the superconductor behaves like a perfect diamagnet. Behaves like perfect diamagnet. In case of diamagnet, the magnetic lines of force is repelled away. The same way, as you can see, the superconductor is also repelling the magnetic lines of force, so acting like a perfect diamagnet. Now we'll be considering various effects such as isotope effect. So before going into this, let me just clarify a few things. So you get the phenomena of superconductivity. You understand it exactly how it is. How it is generating. We'll be talking about them, but for the timing, the condition. The first condition is low temperature. Okay? It should be maintained below a low temperature. So that is Tc. And under this condition, the magnetic field will be 0. Okay. Now, superconductivity can be vanished if you increase the temperature. If you stay above this temperature, you will not get superconductivity. That is why there is so much effort is going on to find out room temperature superconductivity. In past few years, you have seen news of ISC developing room temperature super. So it is not possible. Extremely low temperature is required, around 4.2 Kelvin for mercury, you can see. So scientists are attempting to make superconductor at room temperature. So that will be a significant discovery. So this is one thing, that you need low temperature to create superconductivity. Another thing you have to keep in mind, that is the magnetic field. The applied magnetic field should not be very strong. Okay. So depending on these two conditions, superconductivity criteria will be decided. Now isotope effect. So this critical temperature is found out to be varying based on the different isotopes material of a particular, you can say, element. It has been found out that the critical temperature Tc of superconductor is proportional to the negative half power of isotopic mass of the element. For an that is, if I write it, Tc is proportional to negative half power of the isotopic mass. So you can write Tc times m type half is equals to constant. Okay, you can write, like for example, if I take the example of mercury, in case of mercury, this Tc value varies from 4.185 Kelvin to 4.146 Kelvin, depending on its isotopic mass. Okay? As the isotopic mass m varies from 199.5 atomic mass unit to 203.4 atomic mass unit. Now you see, this critical temperature is varying proportional to m to the power minus half. On the other hand, we have seen that the Debye temperature is proportional to m to the power minus half. Okay, the Debye temperature we have already talked about. in lattice specific heat. So this d by temperature theta d of phonon spectrum is also proportional to m to the power minus half. Okay, so we can combine this two formula. Theta d proportional to m to the power minus half. That means theta d is equals to theta d times m to the power half is equals to constant. Let's say if I name it equation number 1, if I name it equation number 2, or if you just divide equation 1, divide and equation 2, what you get? You get Tc upon theta d is equals to constant. Can I write it? So remember these formulas. Times I get question. These three formulae. How isotopic effect decides Tc, and how d by temperature decide isotopic mass. Let's go for a problem. Given that the transition temperature for ordinary mercury of an average atomic mass 200.6 mu is 4.153 Kelvin, the Tc value for 204 mercury. Can you do this problem? Ordinary mercury is 200.6 Hg. This information I'm giving you extra. So for 200.6 Hg, isotopic mass is equals to, let's say, m1, 200.6 mu, and Tc, let's say 4.153 Kelvin. So for 204 Hg, isotopic mass is how much, and Tc2 is how. So you can take 204 mu. So Tc2 is to be determined. So we know that Tc m to the power half equals to constant. And that means Tc1 m1 to the power half is equals to Tc2 m2 to the power half. So Tc2 is equals to m1 by m2 to the power half times Tc m1 200.6 204 per half, ma is cancelled, into 4.15 Kelvin. So whatever is the answer, that will be the answer. 4.118 Kelvin, approximately 4.12 Kelvin. Option A. Clear? Now let us talk about critical magnetic field. So you have understood critical temperature, right? Now let us try to understand critical magnetic. Let's say we have superconducting wire. Okay. Now if you maintain a temperature below the critical temperature, let's say, okay, so if you maintain the temperature of the superconductor below the critical temperature, so then it will be a superconductor, right? Now if you keep on increasing the magnetic field after after a certain amount of magnetic field, the superconductor will turn into a normal conductor. You see, below this magnetic field, it is becoming a superconductor. It is remaining in the superconducting state. As you enhance the magnetic field beyond this critical value, it is turning into a normal conductor. So that particular value is the critical magnetic. So the summary is, even if you maintain the temperature below the critical temperature, you need to also maintain the applied magnetic field. It should not exceed the critical magnetic. If it exceeds the critical magnetic field, even if you maintain it at low temperature, it will not show the superconductivity property. Okay. So just write few lines. If the magnetic field is applied parallel to the length of the superconducting wire, the resistance of the wire is suddenly, look, below this Hc there is no resistivity because it is a superconductor, and as it crosses Hc it becomes a normal conductor, means it gains resistivity. For normal conductor there will be resistivity, right? So if a magnetic field is applied parallel to the length of the superconducting wire, the resistance of the wire is suddenly restored at a definite magnetic field, definite magnetic field, which is a function of the temperature. If you maintain it at lower temperature, you will need this critical value will be more. Okay, so which is a function of the temperature. I will give you a relationship, and is characteristic of particular metal. So it is not fixed for all the metals. Depending on the metal, this value will keep on changing. So that particular field is known as the critical magnetic field. Critical magnetic field, H. Now it is given by, mathematically we get this relation Hc, this is equals to Hc 0. What is Hc0? You can easily understand what is Hc0. The critical magnetic field at 0 Kelvin temperature, okay, into 1 minus T by Tc whole square. Obviously, if you put T equals to 0, Hc will be equals to Hc0. So at 0 Kelvin temperature, the critical field will be Hc. So this relation you have to remember. It's a very important relation where this Hc 0 is the critical magnetic field at absolute zero. Absolute zero. Absolute zero means 0 Kelvin. So the one graph we got for the resistivity versus temperature. So we have seen that at a temperature of Tc, the resistivity value decreases. Here also we'll be getting a curve like this. If you put resistivity along y-axis, magnetic field along x-axis, then at a critical magnetic field Hc, the resistivity will drop down to. Now can you tell me one thing, if the critical magnetic field okay, so if magnetic field is applied, critical value or critical temperature will decrease or increase. If magnetic field is applied, if there is no magnetic field, you have got Tc. If you apply magnetic field, Tc value will decrease or increase. Understood? At H equals to 0, and there is no magnetic field, we have got T is equals to, so we got, let's say Tc equals to, now if you apply some magnetic field, Tc will be Tc prime, so whatever value we will get, this Tc prime will be less than Tc, means you need further lower temperature to get the superconductor, so it will be decrease. Good. If magnetic field is applied, the critical temperature decreases. चलो एक प्रॉब्लम करते हैं. Let's do this problem. The critical magnetic field of superconductor at temperature 4 Kelvin and 8 Kelvins are 11 milliampere per meter and 5.5 milliampere per meter. The transition temperature means critical temperature is. Look, Hc at a particular temperature is equals to Hc at 0 temperature into 1 minus T by Tc whole square. Look, this is whole square is inside this. It is only T by Tc. Don't confuse it. Like 1 minus T by Tc whole square. It is not like that. It is 1 minus T by Tc whole square. Okay. So as you can see, Hc1 is equals to 11 milliampere per meter and Tc1 it is equals to 4 Kelvin. Hc2 5.5 milliampere per meter, Tc2 8 Kelvin. So you have to find out the transition temperature. Acha, sorry. This is not Tc, this is a temperature T. T1, T2. You have to find out. So from the first one, 11 is equals to, let's say Hc0 into 1 minus T is T1 4 by Tc whole square. Second one, 5.5 is equals to Hc0 into 1 minus 8 by Tc whole square. We can write, we have to find out Tc from these two relations. Let's say this is 1, this is 2. So if you just divide 1 by 2, so 5.5 into 2 is equals to 11, right? So 11 by 5.5, that is 2. Hc0 getting cancelled is equals to 1 minus, you see 4 by Tc whole square divided by 1 minus 8 by Tc whole square. From this we have to calculate the value of Tc. So 2 minus 2 into 8 by Tc whole square is equals to 1 minus by T. Let's do it here. This is equals to 2 minus 1 is 1 equals to 1 by Tc square 2 into 8 square minus 4 square. Can you write it? That means Tc is equals to square root of 2 into 8 square minus 4 square means 6. Whatever is the answer, that will approximately 10 point. Clear? Now 10.58 BS. Now you see there is something called penetration depth. We have told you that the magnetic field inside a superconductor, if you have, let's say, superconductor, then the magnetic field is 0 inside the superconductor. So there was a scientist named London. According to him, the magnetic field is not suddenly drops to 0 at the surface, but it slowly drops, then it becomes, okay. So in this picture it is shown very clearly. You can see this is the magnetic field outside B naught, and you see this portion is the magnetic field region. This portion is the superconductor. So as you can see, the magnetic field is not suddenly dropping to 0 at the surface. It is varying in this way. B of x is equals to B naught. It is exponentially decaying. And as you can see, at a particular value of x, it becoming B naught by E. So 1 by E times of the magnetic field at the surface. So that particular distance is known as the penetration depth. Okay. So we're not going into the derivation, but we are just telling you the fact. So London suggested, London is the name of a scientist, not the city. Okay. London suggested that applied magnetic field does not suddenly drops to 0 does not suddenly drop to zero at the surface of the superconductor, but decays exponentially according to the equation b of x is equals to b naught e to the power minus x by lambda. In terms of h, if you write h is equals to h naught e to the power minus x by lambda. Here lambda you are using, that is known as the penetration depth. So to find out lambda, you can easily do this. If you put at x is equals to, let's say, lambda h is equals to h naught by e. Can I write it? H is equals to h naught by e. X e to the power minus 1, so h naught by e. So from this we can define the penetration depth. Okay. Therefore, the penetration depth is the distance at which h naught equals to h naught by e. Clear? Just imagine something like this. So let's say this is the cutout of a superconductor. This is the surface. This is the surface of the superconductor and this is the body, let's say. Now, initially, this is the magnetic field, let's say, applied on the surface, B naught. This is B naught is applied. Now, while entering, so this is B naught. Now, while entering, it will fall exponentially inside the material. And let's say at a distance of lambda, it will become B naught by E. Murli, that's a very good question. B is equals to 0 inside the material. It is, we are talking about the surface, a very small region at the surface. Although we are showing it, it is like mostly it is into the material, but it is not like that. It is surface. What does it say? That the magnetic field does not suddenly drops to 0 at the surface, but it decays exponentially. So in the inside it will be 0. Okay. Understood the difference, Murli? I also got the same confusion while I studied it. It is talking about the surface. So after traveling certain distance, it becomes 0. not immediately at the surface. Just at the surface, little bit the magnetic field lines can penetrate. Actual scenario is like this. So it can penetrate little bit. So obviously, if you can take it to 0 Kelvin, then this will be reduced. If the temperature, let's say T equals to 0 Kelvin and T equals to, let's say, 3 Kelvin. So obviously, if T equals to 3 Kelvin, a little more field lines may enter, but B is equals to 0 inside. Okay, so you can understand it in this way. Now there are two types of superconductor, type 1 and type 2, type 1 and type 2. Type 1 superconductor, type 1 superconductor is also known as soft superconductor, and type 2 is the hard superconductor. Now, as I told you, this phenomena that a magnetic field can enter, so penetration depth is there. Now, sometimes the superconductor can act as a perfect diamond. So that is why there we got two types of superconductor. Like how much magnetic field lines can penetrate. Okay. Now the type 1 superconductor is that in which you will get complete Meissner. Okay. So superconductor which exhibits complete Meissner effect. Complete Meissner effect, that is, they are completely diamagnetic, are called type 1 superconductor. Okay. So for type 1 superconductor, the transition is very smooth. As it crosses a particular magnetic field value, the superconductivity property disappears. So if I, let's say, plot magnetization versus A, because you see the value comes negative, that is why we are plotting minus M and H, so that we get curve like. So for type 1 superconductor, okay, you get this behavior, the value of Hc. This is for type. Now for type 2, second one is यहाँ पे लिखना, overestimation of. Second one is type 2 superconductor. This is known as hard. So for this superconductor, let's write SC for superconductor. For this superconductor, for applied field below, let's say HC1, the material is diamagnetic and beyond that it behaves like a normal. Okay, so you can see this is normal region, this is normal region, and this is your superconducting. Now for type 2, how you get it? Same thing for type 2 will not be like this. It will not fall sharply like this, but it will fall just a moment. Okay, so you see this will completely touch. Okay, this straight line comes from, it is because m by h equals to minus 1 na? M by h equals to minus 1. You can say minus h minus m is equal to, it is like y is equals to mx, the straight line. Okay, now you see for this case the magnetic field is not suddenly zero beyond this HC1. Beyond HC1, you see the superconductivity is starting to vanish. So in this region it is a mixed state, mixing of superconductor as well as normal conducting region, and here we get the complete destroyer of the destroy of superconductor. So you can see it has three regions. One is this region 1. Here it is behaving like a, beyond HC1 it is behaving like a mixed mixed state of superconductor normal conductor, and beyond Hc2 is behaving like a normal. Okay, so this thing we can also show the help of critical temperature plot. Okay, let's say this is H and this is the temperature scale. This is the temperature scale. This is the scale for H. So this is 0. Let's say this temperature is Tc. Okay. So you are keeping under Tc. So this value is Hc1. So here you will get complete Meissner effect. Here you will get complete Meissner effect. Complete superconductor between Hc1 and Hc2. This is the mixed state. Mixed state, or is also known as vortex state. And beyond Hc2 there is no superconductivity left in them. Okay, this graph has the parabolic. Now if you compare and if you find out the relation between Hc and Hc1 Hc2, found out that Hc is equals to square root of Hc into. Okay, is there any question till now? Now to mathematically define type 1 and type 2 superconductor, we need to define coherence length. Okay, so if a material has a superconducting region and a normal region, as you can see, superconducting region and the normal region, many of the superconducting properties disappear gradually. Okay, not instantaneously, gradually over a distance xi. Upon traveling from the former to the later region, this distance is called superconducting coherence length, or Ginzburg-Landau coherence length. So we have got two things. One is London penetration depth. Okay, the penetration depth or London penetration depth, that is lambda L, let's say. And now we have got coherence length psi. So depending on these two values of a particular superconductor, we can define type 1 and type 2. Okay, let's say if the ratio lambda upon xi is greater than 1 upon, then we will call it type 1. And if lambda upon xi is less than 1 upon 2, this is known as type 2. So just remember, now regarding the value of Hc1 and Hc2, because for for type 1 there is no issue, for type 2 we have to keep in mind few. Okay, so let's draw type 2 again. We have minus m along y-axis and h along x-axis. So it is like this. It should have gone straight. So that is a particular parameter. 1 upon root 2. That is a particular parameter. Remember for the time being. This is your Hc1, this is your Hc. So it is like here it is perfect superconductor. Here the superconductivity it starts destroying, so it is a mixture of superconductor plus normal conductor, and beyond Hc2 it is becoming normal conductor again. Okay, so we'll define later a term called phi naught. Okay, this is known as flux quantum. Flux quantum. It has a value E by H by 2E will later for the timing, you know. So for this one, Hc1 has a value approximately flux quantum phi naught divided by pi into lambda square. Okay, lambda you know penetration depth. Hc2 is equals to phi naught flux quantum by pi psi square. Psi is the coherence length. So these two formulae are very important. Remember. What kind of question you can get? Let me show you one of the problems. This came in June 2011. You can see the flux quantum, known as fluxoid, is approximately equals to 2 into 10⁻⁷ Gauss centimeters. The type 2 superconductor is placed in a small magnetic field, which is then slowly increased till the field starts penetrating the superconductor. Okay. So that is what is happening, right? You are increasing the magnetic field, which is then slowly increased, and the magnetic field starts penetrating the superconductor. Okay, so it will hold down. The strength of the field at this point is 2 by pi into. So what value is this? What value is this? Obviously this is Hc1, because at Hc1 it starts falling. The penetration depth of the superconductor, that is what you have to show. What is given? Given the flux quantum fluxoid value phi 0, 2 into 10 to the power minus 7 Gauss centimeter square. Till start penetrating, Hc1 value is 2 by pi. So what is the penetration depth? So you know the value of Hc1, 2 by pi lambda square. So 2 into 10 to the power minus 7 pi. अच्छा क्या निकाल ऑप्शन यू आर गेटिंग पेनिट्रेशन लैम्डा निकालना है ना तो Hc1 is equals to lambda is equals to square root 2 10 to the power minus 6 10 to the minus 6 centimeter. It means how much? 100 into 10 to the power minus 8 centimeter. 100 angstrom. Option A. देख रहे हो दोस्तों कितना ज़्यादा जगह था। आगे बढ़ते हैं। इफ सेम क्वेश्चन here, the applied field is further increased till superconductivity is completely destroyed. It has been further increased till the superconductivity destroyed. So Hc2. Strength of the field now 8 by pi. So Hc2 value is given to 8 by pi 10 to the power 5 Gauss. The correlation coherence length of the superconductor. Tell me. Hc2 fluxoid by pi xi square. Xi is equals to fluxoid by pi Hc. Fluxoid value already know it. 2 is 8 by pi. This is equal to 1 by 2. Then the 1 is 6 and 0.5 100 half of 100. See? Now we need to know two equations. London, those are called London equations. Okay, so just write few lines to London equation. According to the London theory, it is assumed that there are two types of electron. There are two types of conduction electron in a superconductor. Look, in a normal conductor, what the electron will be called normal electron. So inside the superconductor, electrons are only there, na? When they are in a superconducting region, we'll call them superconducting electron. Conduction electron in a superconductor. What are those names? Namely, the super and normal electron. So at 0 Kelvin, which electron will be there? All the electron will be super electron. And beyond the critical temperature, all the electron will be normal electron. And in the mixed state, there will be mixing of superconducting and normal electron. At 0 Kelvin, okay, it's superconductor contains only super electron. That is quite obvious. And as the temperature rises, the normal electrons increase, and above Tc, all the electrons are normal electron. This is quite a straightforward thing, logical thing. So if I name, what is this n n n s, what are these things? So you can say that this is the density of normal electron. Okay, n density of normal electron. Ns will be density of super electron. You see, there are a lot of things. I'm just trying to make it as simple as possible for you, so that with minimum effort you can have maximum gain. Vn and Vs in a similar manner we can define as the velocity of normal electron, and this is the velocity of super electron. Now London equation 1, djs, you can see, you can imagine what is js. Js is the current density for super electron. djs by dt, this is equals to ns e square capital E by m. This equation is known as the first London equation. All the terms you can understand, djs by dt equals to ns e square E by m. And another equation we have, curl of js is equals to minus ns e square mu naught h by m. M is the mass of the electron and London. So you can remember these two. So we can derive if you want, but I think the derivation is not required. You just need to, if you are interested, you can any book, Puri Babbar, you can refer, get the proof. H is normal magnetic. There is nothing like normal or superconductor magnetic. Only the electron. There may be super electron and normal electron. Other than that, everything is same. Okay. Look, Js is associated to the electron, current density. So it is related to the electron movement. So it depends whether it is super electron or normal electron. But for electric field, magnetic field, these are externally applied, no? So there is no relation with this super or normal. Get it? BCS theory. This is one of the most successful theory for the explanation of the superconductivity. Bardeen, Cooper and Schrieffer theory, also known as BCS theory. Though the London theory explains the two conditions E equals to 0 and B equals to 0, characterizing the superconducting state. In the superconducting state, inside the material E equals to 0, B equals to 0. But it does not tell about the process happening inside the superconductor. What exactly happening inside the superconductor, so that we are superconductivity phenomena. The process which takes place inside the superconductor is explained by BCS theory. So there are four processes which is happening inside the superconductor. So that gives a good picture of the superconductivity phenomena. The first process is electron lattice electron interaction. You can see electron lattice electron interaction. So in this picture you can clearly see it like one electron first comes, it destroys the lattice, it disturbs the or deform the lattice, and in the deformed state another electron comes. See, when an electron comes in contact to the lattice, it deforms the lattice, quite obvious. And at the same time another electron come in contact to the deformed lattice to take the advantage of the lattice deformation. In terms of it, the lattice also apply a force on this electron. Thus, there will be an interaction between electron and electron in which the phonon or the lattice vibration acts as a mediator. So you can see in this picture, first one electron comes, it deforms the lattice, and in the deformed lattice, when another electron is coming, this lattice is interacting with this electron. Okay. Second is Cooper pair. This is one of the mostly used terms in superconductor. The fundamental postulates of BCS theory is that superconductive phenomena occurs when the attractive interaction between two electrons. So you know electron generally repels, but under certain condition, two electrons can make a pair. Okay, and in that scenario, they attract each other. This is known as Cooper pair. When the attractive interaction between two electrons by means of a phonon exchange, attraction is happening via phonon exchange, dominate the usual repulsive Coulomb interaction. Obviously both are negatively charged, so they should repel, but if the phonon exchange dominates this repulsion, they will stick together and they will form Cooper pair. You know electron is fermion or boson. Electron is a fermion, spin half. But when electron pair is formed, Cooper pair, it forms a Cooper pair. So it becomes a boson, right? The spin becomes integral, right? For fermion it is spin half, but when for two electron, spin may be 0 or 1. Okay? Let's say 0 if you consider that they are having opposite spin. So 0 means boson. Two such electrons which interact attractively in the phonon field are called a Cooper pair. These Cooper pairs behave like a single particle. The energy of the pair of electrons in the ground state is less than that energy in the pair in the free state. That is why they can form the pair. You see, if you consider the electron energy, another electron energy, you take the total, and when they are bound, this energy is less. Okay, that is why this formation is possible. The energy of the pair of electrons in the ground state is less than the energy of the pair in free state. The difference of this energy of the Cooper pair, and that is the energy of the Cooper pair, and that is the energy that of the Cooper pair, and that of free electron is equal to the binding energy of the. Okay, so this difference in energy, you take the energy separately and you calculate the energy. So what is the difference? That difference energy is the binding energy of the. So at temperature less than Tc, electron lattice electron interaction is stronger than electron, and pairing is complete at T equals to 0 and completely broken. So between 0 to Tc, this Cooper pair will exist. As you go beyond Tc, Cooper pair will vanish, and at T equals to 0 will be strongly bound, strongest. You can see the spacing between the two electrons is of the order of 0.1 to 0.49. You can see it's a very narrow, very fine distance. Phonon interaction can go up to 100 nanometer. So the process of forming Cooper pair is shown. So one electron came, another electron came, they deform the lattice. They interact via the phonon exchange and they form a pair. You can see oppositely spin, so the total spin is 0, acting like a Look, with picture it becomes very easy for us to. Now this energy difference between the free state of electron and the paired state as the energy gap at the Fermi. So band gap energy of superconductor is this: electron separated, total energy, electron forming pair, the energy. This gap it serves as the band gap of the superconductor. Okay, this is a little unconventional. The way we understand the band gap of semiconductor, it is a little bit different. Here it is this difference between the free state energies and the Cooper paired state energy. That difference is served as the band gap. This gap is maximum at absolute zero, obviously, and becomes zero at t equals to t critical. You can see this is the energy gap of. So the general formula is Eg, band gap of superconductor. Sometimes question come from band gap of superconductor Eg equals to around 3.5 or 7 by 2 kb into T. kb is the Boltzmann constant. Bc is the critical temperature. So this energy gap you understood. Another point is there in BCS theory, paired electron. The Cooper pair are not scattered. This Cooper pair is responsible for the superconductivity. So if I summarize the whole thing, you have the lattice. Okay, you had the lattice. One electron came, it deforms the lattice. So under this in the deformed lattice, another electron comes. So interaction happens, they form Cooper pair. Okay, Cooper pair. Now Cooper pair is special. Why special? It is not scattered while traveling through the lattice because of the special property of smooth riding over the lattice imperfection without exchanging of energy with them. When they are forming Cooper pair, they will not exchange energy with the lattice, and that is why their resistivity becomes zero. When resistivity will come, you imagine you are running from one end of the field to the another. Okay, now if there are many people on the way, while you are going, you may encounter maybe scattering. Okay, but if you see there in the field you are going and there is no people in between you and your destination, so you can move freely. So it is like that, it is not interacting with anything. So that is why resistivity, it is not experiencing any resistive force. As a result of this, they travel a certain distance in the coupled motion. That distance is coherence. So we don't think that once a pair is formed, it will maintain this pair indefinitely. No, they will travel some distance and they will break apart. Okay, so that minimum distance, the distance which they travel, is known as coherence length. So the distance which they travel in the coupled state, that is the coherence length. It is of the order of 10 to the power minus 4 centimeter. So you can imagine how small, less than a millimeter. So there is a relation. This xi0 is equals to h cut Vf by pi Eg. This is the band gap Vf is the time space, and this one you will already the coherence. Energy gap is comparing between free electron pair and Cooper state. Not comparing, it is just the difference. You calculate the energy of the free state electrons. You calculate the energy of the pair. This is low, obviously lower energy, right? So this minus this, whatever you get, that is the source of find energy gap. So whose value is 3.5 kbTc or 7 by 2 kbTc. So what is this order of energy gap? It approximately 1 millielectron volt. In superconductor you have seen it is around, in semiconductor you have seen for silicon around 1 electron volt, right? Here it is 1 millielectron volt. The order of magnitude of the energy gap of a typical superconductor is 1 millielectron. Look, the band gap in a BCS conductor, superconductor is measured to be 3 millielectron volt at 0 Kelvin. The critical temperature of the superconductor is. Can you do it? Okay, one thing I would like to mention here. Okay. Cooper pair follows Bose-Einstein statistic and it has zero spin. It is already known. You can do it at home, right? You can use this formula. Eg is equals to 3.7 by 2. Okay? Eg is given to you. The option may not match, but whatever you get. AB 1.3810. Okay, so one important line you can write. Magnetic flux through the superconducting ring or conducting ring is one type, and the effective unit of charge is 2e rather than e. Okay, so the magnetic flux phi is n times h by sometimes question mark. This is known as the fluxoid or fluxion. Look, 2e is there. A superconductor ring carries a steady current in the presence of magnetic field B normal to the plane of the ring. Identify the incorrect statement. The flux passing through the superconductor is quantized in units of Hc by E, but it is Hc by 2e. So this is the incorrect. The current and the magnetic field in the superconductor are time independent. This is also true. It is persistent. Current density and B related by this. Also, superconductor shows an energy gap which is proportional to the transition temperature of the superconductor. In Eg to 3.5 or 7 by 2 kBT. Okay, let us talk about thermodynamics. Specific heat changes discontinuously at the transition temperature. TC, transition temperature or the critical temperature. So let's say if you are plotting CV versus, let's imagine this is the transition temperature TC. So what will happen? This is the transition temperature. The superconductivity, the CV value increases in this way. Okay, increasing. Now it suddenly drops. It shows discontinuity and it goes. So this portion is superconducting and this is for the normal. So superconducting specific heat varies linearly. You can imagine the normal one varying linearly with temperature in normal conductor. And exponentially in superconductor, and it is given by, so the superconductivity behavior given by this CV is equals to e to the power minus a is a constant, right? So this is how the specific heat is varied. Now this amount of discontinuity which you get here. This amount of discontinuity is given by Rutger's formula. As per Rutger's formula, the specific heat for superconductivity and specific heat for normal conductor, this is equals to 4 H naught square divided by mu naught. Okay, this formula are not so important, you just remember this. One last topic is remaining, that is Josephson junction. Do you know one thing, that the transition from normal to superconductor or superconductor normal, what kind of phase transition it is? It is second order phase transition. Okay? Superconductive transition is the second order phase transition. Forgot to mention it. Superconductor, normal to superconducting transition. Normal to superconducting transition is a second order phase transition. Phase superconducting phenomena is a second order phase transition. One last thing is left, that is the Josephson junction. So the Josephson effect is the phenomena of supercurrent, current that flows indefinitely long without any voltage applied across a device known as Josephson junction, which consists of two or more superconductors coupled by a weak link. Superconductor, normal conductor, again superconductor. The weak link can consist of a thin insulating barrier known as the superconductor insulating size, a short section of non-superconducting metal SNS, or a physical constriction that weakens the superconductivity at the point of contact, SSS. So this is a Josephson effect. Two superconductors separated by a thin insulating layer can experience tunneling of Cooper pairs of electrons. So you see, there will be Cooper pair in this superconductor, there will be Cooper pairs in this superconductor. So via this small barrier, the Cooper pair can tunnel through. The Cooper pair on each side of the junction can be represented by a wave function similar to a free particle wave. So in the DC, there are two types of Josephson effect. One is DC, another one is AC. In the DC Josephson effect, a current proportional to the phase difference of the wave function can flow in the junction in the absence of which. And in case of the AC Josephson junction, a Josephson junction will oscillate with characteristic frequency which is proportional to the voltage across the junction. Since frequencies can be measured with great accuracy, Josephson junction device has become standard measure. So if I just summarize this whole thing, you can understand it with this picture very well. So we have two superconductors are in between. There may be an insulating material or some other thing. So Cooper pairs can travel. So each Cooper pair will have their own wave function. You know, this is a wave function. In quantum mechanics, we have seen this when while discussing the step potentiality. So this is the sinusoidal wave function, and as it experiences a barrier, we will have the exponential decay, and it is going like this. For this Cooper pair, so it is like the flow of the wave function through this barrier. Okay, just a minute. Right. So DC Josephson junction supercurrent, constant phase difference across the junction. Remember this. Phase difference across the junction will be constant. For AC Josephson junction, oscillating phase difference across the. So the phase difference phi of P is given by phi at G plus twice EVT by H cut. So because of the flow of this superconducting Cooper pairs, we will get superconducting current. So the superconducting current is given by I is equals to IC sin phi 0 twice E by H cut. Okay, actually I equals to IC sin phi of t, and phi of t is equals to phi 0 plus twice E by H cut. So you can see phi of t, so it is like phi 0 plus omega t. So this is like the angular frequency. The current oscillate with frequency. You can imagine it is like omega t. Omega is equals to twice EV by H cut. V is the voltage you applied across the thing. So H cut omega is equals to 2 EV. What does it correspond to? So a photon of energy H cut omega is equals to 2 electron volt is emitted or absorbed when an electron pair crosses the barrier. When a Cooper pair crosses the barrier. Okay, so you can see the Cooper pair crossing the barrier. So 2 electron volt may be absorbed or may be given off. Now you imagine when we send current through a normal conductor, when we send normal current, so they consist of some resistivity, and because of that, when current flows, we will have some loss. Now you imagine superconducting. For superconducting wire, resistivity inside is, so if current flows, this is why so much of effort is given developing this. It is like the way we imagine now. I is equals to I naught sine omega. So sinusoidal current, the AC current, it is like the AC current. I say this is the magnitude. I equals to I naught sine omega. So you imagine it in this way. Sine omega, the maximum current. One question, let's see. A DC voltage V is applied across a Josephson junction between two superconductors with a phase difference phi naught. Okay, if I0 and K are constant, the dependent properties of the current flowing through it. Tell me what will be its answer? Voice is not clear? Voice is not clear? So you see, how do you represent a sinusoidal graph? Okay, na? This is I is equals to I naught sine omega t, right? So the maximum value we are getting I naught. Okay, and it is oscillating. In the same way here it is I is equals to IC sine phi t. You are applying voltage difference V with the phase difference of phi naught. Then the current which is flowing through this link that varies in this. I is equals to IC sine phi t. So I naught sine phi t, phi naught plus omega t. Omega is equals to 2 electron volt by h cut. Okay. So sometimes these questions come, or sometimes question may come like if you have a superconductor here and it is connected by some insulating link. Now if one Cooper pair crosses this, how much energy is released? So the answer will be h cut omega is equals to 2 electron volt. So if one Cooper pair crosses the barrier, 2 electron volt of energy will be released. Is everything clear? Time for college journal part. Oh, so okay, we are at the end of this lecture, and I think we have covered everything from so. If you have any question, you can ask. Oh, option A. Yes, yes. When will you get the order mic? Yeah, just delivery message. Option A is the answer. Yes. So your all the 100 topics is over. I will take a little bit of gap, okay, for a few days, because the theory portion which you require is almost over. So it is the time to practice. So you practice it from the test papers, okay, test series which I have given you. Lot of test series I am running. No, CSR net test series you will get tremendous amount of questions. GATE test series is there, and recently we are also conducting BRC test series. So on all these test series, questions are different. Okay, it is not like same questions are given in the all the test series. Questions are all different. So practice as many questions as possible from the test series, and I hope you will be easily able to understand whatever theory you have done till now. Based on that, you will be able to understand them all. If you find any difficulty in any question, you can DM me on WhatsApp. I will definitely help you out. Okay. After a few days, after the break of few days, I will start taking some practice sessions, and maybe quantum mechanics we can start. Okay, I think your GATE exam is nearby, so give your GATE exam, then we can start. Hello, bye bye. Take care, guys.